one question for homework last night. It was page 599, question number 1. Are we okay with that? We weren't trying to find a direction or anything, right? That's a pretty straightforward question, I think. In the end, if we're trying to find a magnetic force on a charged particle that's moving through a magnetic field, and the charged particle is moving perpendicular to the magnetic field, then this equation applies. The only other situation we're going to come across is if the charged particle is moving parallel to the field. And if that's the case, then we know that the force is equal to 0. So we're either going to say it's 0, or we use this equation, and that's going to give us the force. In this case, it tells us it's perpendicular. Use this equation, we get our answer. Good there? All right, let's try another example then with that same concept that we did yesterday. 12.2 on page 600. This one says a carbon ion, which we've never really seen before, a carbon ion, has a mass of 2.01 times 10 to the negative 25. 10 to the minus 26, that should be. Kind of hard to read that number there. It's got a positive charge. Let's underline that or circle that in red to remind us that it's a positive charge. And if we have to use a hand rule, we're going to use a right-hand rule. Whichever hand rule it is, it's going to be a right-hand rule. It enters the magnetic field. We want to find the speed at which the deflecting force will balance gravity such that the carbon ion will travel in a straight line. Force will balance gravity. There's a word there. There's a word in that question that, from my perspective at least, tells me exactly what to do. Anybody see that word? Anybody notice that word? Simon, put your hand up. That's what I saw as well. Okay, I thought that word balance tells me exactly what to do. If I've got a magnetic force that balances gravity, what do you think I want to do, Simon? Okay, and then do what? Not the charge, but the magnetic deflecting force balances the gravitational force. So let's say the magnetic force is equal to the gravitational force. Now, you said find the gravitational force and then set it equal. Doesn't really matter whether we do that or just set them equal right off the top. Okay, it doesn't make any difference in the world there. I tend to like to set them equal right off the top, but there's no good reason for that necessarily. The magnetic force here is QVB equals m times g. You know what? Before we go through this, let's make sure that this is even possible. We know that the force of gravity acts down. Let's make sure that the magnetic force acts up, right? It has to in order to balance, but let's just make sure that it can. We're going to stick our right thumb, because it's a positive particle, in the direction of the particle, which is into the page. Our fingers are going to point in the direction of the external field, which is from north to south. Our palm will point upwards. Sure enough, gravity is down, magnetic force is upwards. They can balance each other. Okay, so back to the math there. QVB equals m times g. We're looking for the speed at which this can happen. So V ends up being equal to mg over q times b. 2.01 times 10 to the minus 26 times 9.81 divided by 1.6 times 10 to the minus 19, same as the charge of a proton, times 6.32 times 10 to the minus 5. Now that's a pretty weak magnetic field for two bar magnets, but it's possible. Just really weak. It's about the strength of the Earth's magnetic field. Let's do this on our calculator to make sure that we can do it here. Let's get the top number there, 2.01 times 10 to the minus 26. Let's multiply that by 9.81. Let's divide that by, use some brackets here, 1.6 times 10 to the minus 19. And 6.32 times 10 to the minus 5. We get 1.81 times 10 to the minus 2. Anybody else get that number? Just seems small to me. 1.6. One of us has entered a number wrong then. Because if we're both getting the same order of magnitude, then it's not a matter of doing something wrong, division or order of operations or something like that. It's a number wrong. We just got to make sure, we got to see which one it was, you or me. 2.01, 9, oh yeah, it was me, because I went 9.1 instead of 9.81, right? So what did you get, Simon? So we both got it wrong, that is what you're saying. Okay. 2.00 times 10 to the minus 2. Thank you. Good. If you ever see that word balance, if you see the word suspend, if you see that word hover, anything that means something like balance and gravity, set something equal to gravity. Whether it be an electric force or a magnetic force or whatever force it happens to be, set it equal to gravity. Because that's what you're going to do every time you see that. Okay, balance, suspended, maintains the same vertical position, and so on and so on and so on. Set the two equal to each other, just like that one. All right? Let's see what you can do with these two questions on page 600, please. Let's just go as far as 2A. Take a look at 2B in a few minutes here. Just do 1 and 2A yourselves. All right, guys. If we have no trouble with any of those questions, I would like you for homework for Monday. You got an assignment due tomorrow, so we're not going to assign this for tomorrow. For Monday, I would like you to do worksheet number 11, please. Got it? For Monday, worksheet number 11. Let's take a look at a multiple choice question here. We won't bother submitting this, just in the interest of saving a little bit of time here. Our multiple choice number 72 in your worksheet booklet here, it says moving electrons can be deflected by electric fields, by gravitational fields, and by magnetic fields. One electron is allowed to enter each type of field as shown below. So we got 3 fields, field 1, field 2, field 3. One of them is an electric field. One of them is a gravitational field. One of them is a magnetic field. We want to determine which one is which. I'm going to give you about 60 seconds to determine which field is which. Again, don't worry about submitting it. Just get an answer, commit to an answer, and then we'll take a look at it as a group here. What do we say the answer is to this question? Who says A? 1, 2, 3, 4, 5, 6, 7 of you. Okay. Who says B? B? 1 of you. C? D? 1. Okay. So overwhelmingly, we're saying the answer is A. Let's check here. Here's my strategy for solving this question. I look at what the easiest field is to deal with. What's the easiest of the 3 fields? We got gravity, we got electric, we got magnetism. What's the easiest of the 3 fields? I would say gravity is the easiest. One, because it can only be one direction, right? It has to be pointing toward the producer. And then whenever I want to find which direction it is, all I have to do is put a mass in that field, let it go, it will move in the direction of the field. Whereas, got to be careful with the electric fields, if I put a positive in a field, it goes one way, put a negative in a field, it goes the other way, and so on. So gravity is easiest to deal with. Let's try to find the gravitational field first. If I want this particle to be deflected downward, this particle with mass to be deflected downward, which way does gravity have to point? Down. Right? Gravity has to point down if I want this particle to move downwards. So that means field 3 is going to be gravity. A downward field causes a downward force. Now, what's the next easiest field to deal with? Electricity or magnetism? Magnetism? Who agrees with that? I mean, in the end, it's all a matter of personal preference. Like, there's no wrong answer to that question. I'd say electricity, actually, personally. Because I think, look, you get a negative particle or a positive particle with electricity, it always experiences a force with the field or against the field. With magnetism, it's perpendicular to the field. You got to use that hand rule, right? So I think electricity is easier. But if you find magnetism easier, that's fine. Okay, it's all a matter of, again, your own personal take on it. Let's do magnetism then, okay? If a couple of people are saying the magnetic field is easier to deal with, then let's do that one. I want this particle to be deflected downwards. Which way do I have to have the field to experience a downward force? We're going to say thumb in the direction of the particle, which is to the right. I want my palm to point downwards here in the direction of the magnetic force, right? Which way does the field have to point? Thumb, palm, fingers point. The direction of the magnetic field is? It's a hand rule for deflection here, right? Caitlin, right? It's hand rule for deflection, so its fingers are going to be straight. Thumb to the right, palm down the page in the direction of the magnetic force, because we want them all to experience a force down the page, right? Fingers are going to point into the page. So the magnetic field is going to be which one? This one, right? That's a magnetic field into the page. Well, then the other one must be electric then. But let's just double check that. If we want a negative particle to experience a downward force, which way does the field have to point if it's an electric field? Opposite to the direction of the field, right? So this one's going to be the electric field. So fields 1, 2, and 3 are going to be electric, magnetic, and gravitational. Is that what you guys said? A? Okay, good. So A is our answer then. Okay, I want to spend just a couple of minutes here, guys, looking at these charged particles in the magnetic field a little bit more deeply here. Okay, we don't want to just find the force now. We want to find the shape of the path that they take. I'm going to introduce a magnetic field that's going into the page here, represented by these X's. So that's my magnetic field. I've got, let's make it an electron that's going to the right through that magnetic field. Okay, we can find the direction of the force on that electron easily, right? It's going to be the hand rule for deflection. We got an external magnetic field. We got a moving charge. We want to find the force. It's the hand rule for deflection. Thumb in the direction of the particle, fingers field, palm points which way? Palm points, Maddie? Down the page, right? So the magnetic force here is down the page. We're going to say red is going to represent the force, and we're going to say green is going to represent the velocity. So it's moving, in this case, to the right, but it experiences a force downward. Well, what's going to happen to this electron if it's moving to the right, but experiences a force downward? Is it going to go straight down? No. Is it going to go all the way to the right? No. So what's going to happen to it? Where's it going to go? How about somewhere in between? Right. If you stand up at the front of the room here, I won't ask anybody to volunteer because we've only got a couple minutes left here, but if you're standing up at the front of the room and you walk towards my desk, but I push you toward the back of the room, where do you go? Well, you don't go towards my desk. You don't go towards the back of the room. You end up going over there somewhere in between, right? There's a velocity to the right. There's a force downward. It ends up going somewhere in between. That means the particle is now going this way. It's now going down and to the right because of that force. But now there's a new force. Okay. Now we're going to say thumb down and to the right in the direction of the particle. Fingers into the page. Force is going to point this way, kind of diagonally, left and down. There's the direction of the force. Where's the particle going to go now? If there's a force down and to the right, a particle's moving down and to the right, there's a force down and to the left, the particle's going to go down. Which way is the force now? Thumb, fingers, palm points this way. Particle's going over here. Thumb, fingers, palm points this way. What do you notice about A, the magnetic force? It's kind of crazy here. The magnetic force is going in all kinds of different directions, right? It is, but it isn't. It's always pointing to the same place. You notice that? Regardless of where we're finding the magnetic field, it's always pointing to this place right here. What do you notice about the shape of the path here? What's the shape of the path of this electron? Circle. When something goes in a circle, and there's a force that always acts toward the center of that circle, what do we call that force? The centripetal force. So we have a magnetic force here that's always acting toward the center of the circle. That magnetic force, therefore, could also be called the centripetal force. Therefore, we could, if we wanted to, set the magnetic force equal, well, let's go the other way around. Doesn't matter, but we could set the centripetal force equal to the magnetic force. In Physics 20, you guys learned that the centripetal force is not a fundamental force. It's always caused by something else, always. In the case of the Earth going around the sun, it's caused by gravity. In the case of my keys going around my head, it's caused by the string and ultimately my hand pulling it toward the center. In the case of the car going around a turn, it's caused by friction. In the case of a charged particle going in a circle in a magnetic field, it's caused by the magnetic force. Listen very carefully to this last thing I'm about to say. Every time a charged particle enters a magnetic field perpendicular, and it almost always will be perpendicular for us, it will go in a circle. Does that change what we did yesterday? Not at all. All the particles that we looked at in the problems that we did yesterday and earlier today, they went in a circle.
Can you come to Mrs. O's office, please? Mackenzie.
We just didn't know that. We didn't need to know that for those problems. We will see problems now where we do need to know that. It hasn't changed anything. We just now know more about the situation that we were looking at yesterday. Does that make sense? Okay, we'll continue this tomorrow, okay? Have a good night, everyone. Remember, your assignment is due tomorrow. Worksheet number 11 is due on Monday. Yeah. Okay, that's it today for today, guys. Hey, guys.